So this was our last class, na? Analysis of algorithm. We are
Yes,
actually in asymptotic notations.
yes, asymptotic notations we had discussed.
Okay, asymptotic notation. There are three asymptotic notations in
Mm.
time complexity analysis. Okay, so the one is your big O, another is your big omega,
Big
and the
omega and
theta.
theta.
So
Yes.
there are three purposes of having these three notations, but mostly we use the big O or big theta or the theta.
Mm.
Okay, most often you will found the notation O, big O. Okay,
Mm.
so in the last class we have already discussed that what is big O. Big O is basically there for defining the upper bound of an algorithm. Means
Yes,
you can say what is the maximum time an algorithm can take
can take.
to produce the output for a input size of n. Okay,
Mm.
so if you draw a roughly graph, say this may be the upper bound, uh, this yellow color or
Yes, yellow color one.
this one will be the upper bound, and this is our the function, means the
Functional.
algorithm. Okay, so it
Mm.
will define the upper bound of the algorithm, that how much maximum time an algorithm can take to produce the output for a particular for certain values of
N
n.
inputs.
Okay, so big O is used to define the upper bound,
Mm.
and for big omega it is the reverse, means big omega is used to define the lower bound of a particular algorithm or a function, and what will be
Mm.
the minimum amount of time. I have already given you several examples for minimum and maximum. Okay, so
Yes,
some algorithms are there which do not need the minimum. Okay, for
yes.
that, for those algorithms we will have the only the big O notations, means the upper bound. For there are some algorithms for which we do not need the maximum, we always need the minimum bound. Okay, so
Mm.
for those algorithms we will use the big omega, and there are some algorithms for which we need both the upper bound and the lower bound. So
That
for
is
those
theta.
theta, for those algorithms we will use theta. Okay,
Mm.
so this was all discussed in our last class. Now there are certain lemmas, or you can say basically these are not formula. Okay, mathematically
Mm.
these are called lemma. Okay, so or a theorem, I can say theorem. Big O, the theorem behind the big O is something like that. Okay, so Fn is our algorithm.
Mm.
Fn is our algorithm. Now, if I say Fn is our algorithm, what that mean? In our previous classes, we explained that every algorithm can be transformed into its mathematical
Functions.
function with respect to time. Okay, with
Mm.
respect to time, to express the algorithm for
Mm.
time complexity. Okay, we can express the algorithm with a mathematical function on n. Now, what is n? N is the size of input size.
Mm.
Okay, so Fn is our algorithm. Okay,
Yes.
now what that mean? Fn, if we can have three things with respect to Fn, if we can have three things with respect to Fn, so that we can say that this inequality means Fn less than equal to this thing, then we can say that Fn is equal to big O of g of n. Now,
GFN.
what are the three things? Three things means we have to find three things. One is your another function gn. Okay,
Mm.
the gn, another function gn, and a constant c, and another positive constant n0.
N0.
Okay, and with all those, if I can say that Fn is less than equal to c multiplied by g of n for all, this is the symbol for all, n greater
Mm.
than equal to n0, then we can say that Fn is equal to big O of g of n. Okay, means for a function Fn, if I can find C, N0 and Gn such that we can say that Fn is equal to less than equal to C multiplied by Gn, means this one for all the values of n which are greater than equal to N0, then we can say Fn is equal to big O of G of n. Okay, means
Mm.
G of n becomes the upper bound of Fn. Okay,
Yes.
upper bound of Fn. Now here you will find that this red line becomes the will is representing the upper bound. This black line representing our function Fn. Okay. Now clearly
Mm.
you can see that the red line states that this is the upper bound. This black line will never touch the red line. Okay,
Mm.
it will never touch the
This
red
is
line.
ascent,
You can say,
ascent,
yeah, asymptotic. This is the asymptotic
asymptotic.
behavior because
Mm.
in mathematics asymptotic curves are two curves which will never meet
Not
to each
made,
other,
never
but
made each other.
they are tends to meet. Means
Yes.
they're supposed to meet to each other but will never meet. Okay,
Mm.
maybe in other words we can say that they will meet in infinity.
Okay.
Okay, they will meet in infinity, which means that they will never meet.
They will
Okay,
never meet.
but they will gradually coming
Close
uh,
to.
closer and closer, but they will never meet. Okay, so but you can find that here is a point now where they meet, where
Mm.
they previously met. After that, they will never meet. Okay,
Okay.
at this cross section means this point defines the
Mm.
value n0. Okay,
Mm-hmm.
this is the n0. When see here, fn is less than equal to c multiplied by g of n. Now,
Mm.
if I say that fn is less than c multiplied by g of n, then you can say that they will never meet, or they in past they had never met. But when I say that fn less than equal to, means
Mm.
somewhere they have been met. Equal to means somewhere they have
Somewhere
been met.
they have been
Now
equal.
where they have been met, they met at the point n0, and this is the
Mm.
point n0 where they met. Okay,
Mm.
but after that, whenever whatever value you can put for n, they will have a perfect difference between, means they will have differ to each other, they will never meet. Okay, so these are
Okay.
all the observations that you can find from this graph. Okay.
Mm.
Okay, so this is an example. If suppose fn is equal to 3n plus 2, then we can find in this way, and we can say that fn is equal to big O of n, because we took gn is equal to n. Okay, why I am saying
Mm.
all these things, because the next operation big omega is will be similar, very much similar to this. Okay,
Okay.
so next, the rate of growth means how a function or how the time taken by an algorithm
Mm.
increase with the value of n. Okay, as the value of n increase, the time will also increase. Okay, so that is called rate of growth. Means if you think that, just normally think sum of how much time it will take to find the sum of two numbers, a
Just
certain
to
time, just it will take a time. Okay, but
fraction of
if
something.
you are going to find the sum of say four numbers, then obviously it will take more
Little
time
bit
than the
increasing.
previous. if
Mm.
you if you want to find the sum of 100 numbers, then obviously it will take. So the time is gradually increasing with the number of input, as the number of input increases. Okay,
Yes.
so how much the rate, what is the rate of this growth, that have
Mm.
to be calculated to identify a suitable algorithm for us for a particular solution. Okay,
Mm.
so that is called rate of growth. Suppose if an algorithm is defined by this, fn is equal to 10n square plus
It's
2n
great.
plus n 1. So this is a function. Okay,
Yes.
so in this function you will find that three terms, there are three terms now, 10n square plus
Yes.
2n plus 1.
Mm.
So I can say that these three terms individually they are contributing something. Na?
Yes.
for the value of Fn. They are
Yes.
individually contributing something. That's why their accumulate figure means the plus. Plus means what? Whatever
Adding.
contributed by the first term is added with the
Added to the second
contribution
term.
second term and the third term. Okay. So
Mm.
individually they are contributing some amount of time or
Mm.
some value. Okay. Now if you consider each of the values separately here, see here 10n square 2n plus 1. Okay.
Mm.
So as the n increase, you can
Mm.
clearly see that the value of this 10n square is increasing rapidly, more rapidly than the other two.
Yes.
Okay. So for the higher values of n, means when n is really large, say thousands and millions and billions, then the contribution of this term, that means the first term, is
Is
very much
more
more than the other two.
compared to the other two.
So in case of comparison, since the whole thing, this time complexity is about comparative measurement, I cleared it in the first class. Okay.
Mm.
So we can always ignore the last two terms. Okay.
Yes.
So to find the rate of growth, we can always discard or ignore those terms
The
which are
last.
contributing much, much less than the other term. Okay.
Yes.
And to find the final solution or the final term, we can always ignore the contribution of the constant terms, that is the 10 to
Two.
something. Because in
Mm.
10n square, you can find that in 10n square, the contribution of 10 by itself is constant. Huh?
Yes.
So we can ignore that too also. Okay. So what remains then? Only n
Big
square.
n square.
So to find the time complexity or the rate of growth for Fn, we can put the notation with the big O
Big O.
within bracket n square. That's why we use the term n square. Is it okay?
Mm. Yes.
So Fn is equal to big O of n square. Okay. How can we write that Fn is equal to big O of n square? This is one way and this is another way. Okay. This is the
Mm.
way how you can find the Fn by using the lemma. Okay, by using some mathematical a
Theorem.
little bit computation, and this is
Mm.
rate of growth basically. Okay, the purpose is
Mm.
the same. Okay, to find the
Okay.
value of big O for any algorithm, that is Fn. Okay, so today
Okay.
we will find okay, so this one is a scale, you can say a scale. Okay, so rate of growth for this algorithm is big O of n square. Now suppose I tell you that I have another similar type of algorithm which works the same thing. Means suppose this algorithm, this Fn, okay, this Fn algorithm is a sorting algorithm, okay, and
Yes.
I am telling you that I have another sorting algorithm which has the time complexity or the rate of growth big O of n. Okay,
Mm.
suppose you want an algorithm which can sort your inputs.
Input.
Okay, sort your data. You have one solution Fn, and I am saying you that I have another solution. Okay, say let's f dash n,
Mm.
and then obviously you will ask me what is the rate of growth of your algorithm,
Yes.
because I have already an algorithm which has the rate of growth as big of n square. Then I am saying, then I will tell that see I have another algorithm f dash n which has the rate of growth as big O of n.
Mm.
Then how can you compare to choose the best algorithm for your purpose? You will look into this scale. Then you will say me, okay, just give me a minute, and you will look into the scale. Here you will find that big O of n is here now.
Yes.
So big O of
Third
n
term.
is less than big O of n square.
Mm.
So your algorithm, whatever you have in your hand, has
Mm.
the rate of growth big O of n square, and what I am giving you is big O of n. So you will tell me, okay, give me your algorithm. Your algorithm is maybe it will work
Yeah.
better. It will work efficiently. It will take less
Yes.
time, less amount of time. Okay.
Mm.
So this is a scale uh, means we choose algorithm for less time complexity depending on this scale.
Okay.
Okay, okay,
Okay.
fine. Then we move the next part, that is your big O. We are saying big omega. Sine for omega is something like that.
Huh.
Okay, maybe I have not drawn it rightly.
No, it is
It
almost
is something
similar.
like
It is almost similar.
it is something like that. Omega.
Mm.
This is big omega. You have another small omega, na? That look like
Okay.
W. This is small omega. This is big omega. That's why it is called big omega. Okay.
Okay.
So it will also have a lemma or a theorem, and it is something like that. If we have a function f of n,
Mm.
and just a minute, what
One positive number, I guess.
I want to write in the same manner so that you can
Ah.
remember it. Let fn be a function, and if there exist two positive constant.
Here
Okay,
it could be one positive constant, I think.
so
No, or
I will write in this, let f of n is a function, and if there exists
constant
is a function, and if there
will be.
exist
Okay.
exist two positive constants, two
Okay.
positive constants c and n0, c and n0 I will write later with
Mm.
the mouse, and we get another function g of n, and we get another function g of n, such
Mm.
that such that fn is equal to, अच्छा अभी हम we will write it using mouse. Okay, so the same thing, huh? I'm
Yes.
writing in the same word.
F of n is less than or
Hmm.
equal to.
So what I have to write now here, c and n0. Okay, c and n0. Let fn be a function, and if there exist two positive constants c and
C
n0,
and
and
n
we
zero
get another function g of n such that f of n, what will be there? Tell me. F of n will be
will be
greater than
greater
equal
than
greater
equal
than
to
equal to c of g of n, na? C
mm, of
of
g of n.
g of
C
n,
into g of n.
c into g of n,
O.
for
No,
all.
C for all.
This is for all sign,
Yeah.
for all n,
N is greater than
n is greater than equal to n0.
n zero.
Then we can say,
F of n is
then we can
omega.
say,
Big omega. F
uh,
of n is equal to big
then we
omega.
can say f of n is equal to big omega of g
Big
of n.
omega. Ah,
F of n is equal to big omega of
g of n.
n. Okay, so this is the simple thing. Okay,
Okay.
now what it
Yes.
means? This means the same thing. It was the upper bound, and now It
We
will
are
be the
considering the lower bound.
lower bound. Okay, so just take a graph. Okay, suppose this is our fn. Okay,
Hmm.
now this will be our
Gn
gn, and this point,
is G0.
this will be n0.
Oh, sorry, N0. Okay.
This is your n.
N
This will be your t,
is T.
t. Okay, and this difference you can say this is your c. So gn is defining the lower bound of f of n, means the time will not be less than gn at any point of time if you use the function fn. Okay,
Yes.
so if I take an example, say suppose, take an example, say suppose
Hmm.
our f of n, f of n, sorry, f of n is equal to say 10n square.
Same only will take
Yeah, we can say same only.
10n
Second,
square plus 2n plus 1
10n square
plus
plus
2n
2n
plus 1.
plus 1, maybe a function like this. Okay, so
Hmm.
we are interested to find the big omega for this function fn.
Hmm.
So how can we find that? For that purpose we have to consider, we have to find three things. One is your gn,
Gn
another is your
T,
c, and
then
another is
n.
your n0.
N0.
So what will be the value of these three? By inspection you can get it. Otherwise you have to go with a little bit of computation. So by inspection
Hmm.
we can get it. So see what we will take as gn. We will take as gn as n square.
N square.
We will always consider the highest power of n.
Highest
Okay.
power to
After
GFN.
that we will find the value of c and n0. So
C
so that
is
your fn means this one. See, if I can if I write 10n square plus 2n plus 1 is greater than equal to, what will be the value of c of n square for all n
N
greater
is
than equal to,
equal to
we have to
N0.
fill in the blanks, these two.
Hmm.
Okay, so can you guess? Tell me what will be the value. Say if I put
This
n0, this will
0.
be your n0, okay, as 1, then what will be the value? This will be
This
your
will
1,
be
this will be 1,
hmm.
and this will be your 10 plus
Oh,
12,
10 plus
13. Na?
1 square, na? It is
1 square plus 2 plus 1, that means 10 plus 2 plus 1 means 13.
13. Yes.
Okay,
Hmm.
so straightforward, if I put 13 here, then what will
Hmm.
happen? If I put 13
13
here,
will become the G of
13 and n01. So see, if it is satisfying the condition, that means in the left hand side you will get 13 and the right hand side you will get 13. So 13 greater than equal to 13 is true. Now
yes,
if I put 2,
equal
then
to
if I put 2 here, n equal to 2, then what will be the value of here?
20, no,
13 equal
10
greater than
into
equal to 13, first condition is true. Then if I put 2
okay,
here, then this will be your
10, 40,
40. plus
plus
44 plus
4
45,
for 45.
and here it will be what,
45 greater than
equal to
2.
hmm? 2 means 4, 55. No, it is not satisfying. Okay, here you have to find the value so that this condition
Mm.
satisfy for
For
all values of n
all the
greater than of this value.
mm,
Then what it can be?
take something lesser.
Say
That,
if I
that,
put not 13 here, if I take 1, okay, c is equal to 1, okay, then what it will be? Say here it is your 13,
uh,
and here it will be your 1. So 13 is greater
1.
than 1, 13 is
Yes,
greater than equal to 1. After you
yes.
put 2, for n is equal to
Mm,
2, so
mm.
it will be the value of 45. So 45 greater
45
than
is
equal
greater
to
than 2.
4,
4.
right? So if you put
Mm.
3, then this will be something
Again, more
more.
than 45
It will
only.
be, it will be 9, na?
It will be greater than 9.
Greater than
Yes.
9. So I think this will satisfy. Okay.
Mm.
So we put c is equal to 1 and n0 is equal
N
to
is
1.
equal to 1.
Hence we are able to find these three values
Hmm.
for fn. For this function, we are able to find these three values so that this condition satisfy. Okay.
Yes.
So we can say that our fn can
Is
be
big omega
big O of g of n.
g of n.
Now what is your g of n? G of n is your n square.
N square.
So big O of n square. So fn, if fn is an algorithm, so its lower bound is big O of n square. You have to say like this: if fn is our algorithm, then its lower bound is big
Omega
omega of n square. Okay,
n square.
so this is the way how you have to specify the lower bound of an algorithm and upper bound of an algorithm by means of big O, lower bound of an algorithm by means of big omega.
Big omega.
Okay, is it?
Okay. Yes,
Okay.
it's gettable.
So this was your big omega. Next,
Mm.
we will go for theta. Now, where theta is
Both
applied to specify,
lower, both upper bound and lower bound.
yeah, both upper bound and lower bound. Suppose here, what we have done so far, say fn is a, writing here, say fn is a method, na? Fn is a function.
Yes, function.
So for fn, we are trying to find another function
A
gn.
function g of n.
Okay, which is either upper bound or lower bound.
Hmm.
If it is upper bound, then we use it with big O. If it is lower bound, then we use it with
Big,
big omega.
big omega.
But
Now
see,
we want two functions.
no, two functions now. Now see, if we found, if we can find a function gn which is simultaneously acting as an upper bound as well as acting as a lower bound, a single function which
Mm-hmm.
at the same time is acting as an upper bound, acting as a lower bound, then we can say that gn is the theta of fn. Now, how can
Is
it
it
be possible?
how we can take
Yeah,
two
you
methods
can
like
say that
polymorphism?
uh, no, you should not relate polymorphism with it. Okay, we are interested here to find one function for fn
Which can
which
act as
simultaneously acting as a upper
lower
bound
bound
or the lower
and
bound,
lower.
and it is very much possible.
Oh,
See, I am not saying that you are considering only a single function. Okay.
Mm-hmm.
See, this is possible in this way. Suppose this is a function. This is our
Mm.
function fn. Okay.
Mm.
Now we have some function gn. Okay.
Mm.
Now if you multiply, say if you multiply this with this gn,
Mm.
a constant, not a variable. You have to
Mm.
mind that it is a constant. If you multiply
Mm.
the constant with gn,
Mm.
say c1,
Mm.
okay,
Mm.
then
Mm.
the graph will look like this maybe.
Mm.
But if you multiply the same function with some other constant, say c2, again I am saying these are two
Mm.
constants. If you
Mm.
multiply the same function with another constant,
Mm.
then the graph look like this.
Okay.
Okay, so this becomes the upper bound and this becomes the lower bound of this function, and this function will never touch these two lines.
Mm.
Okay, so the same function gn, when it is multiplied with one constant, it is acting as upper bound. When it is multiplying with another constant, it is acting as a lower bound. That time we can say that gn is the theta of fn. In
There
that way,
could be a possibility na, that another constant can go above the constant one. That possibility also may come, right?
I'm not getting you.
See here there are two graphs, okay, which you have highlighted in red color.
Hmm.
One for upper bound and one for lower bound. One is for constant C1 and another graph is plotted C2. So it might be the C2 value can take a graph above C1 constant also, no?
If you multiply the function gn with the
Hmm.
value c2, okay,
Hmm.
then it will produce this graph, okay, this line. But
Why
there is
can't,
a there
can we
is
prove that?
see, you may have another value, another constant c3 that is
Hmm.
go beyond this line. You may have some other value c4, okay, that
Hmm.
may goes above this line, okay.
Hmm.
But you have to choose C1 and C2 in such a way that these will be the minimum distance between the Fn, from the Fn.
Oh, that values we need to find.
Yeah, for the that C1 and
Function.
C2, you have to
Hmm.
find those values.
Hmm. It is
See here,
something like that in linear equation we write like if you add you get this. Something like that we have to make here.
linear equation means what? No, so think in this way. See, here also
Hmm.
you have to find the value of C. Na?
Hmm.
We have to find this C1, so that this condition remains satisfied. Okay, here
Okay.
you have to find two constant so that the
Hmm.
equation remains satisfied.
Okay.
Okay, so there
We
would be a
have
condition.
to okay, we have to choose the values only in such a way that where we get the equidistance from the minimum, the base
Not
function.
equidistance, it is not required to have the equidistance between these two. Okay, it will be
Hmm.
the minimum distance. Means you have a graph, you have another graph, you may have some
Hmm.
other graph, but which one is the closest, you have to choose that value. Okay,
Okay.
let's see. Let me write the lemma first. Theta, it is theta. May be called as a big theta also, but simply we can write theta.
Hmm.
So write in that way.
Hmm. A function, what was
Let
that something?
f
Let
of n
function
is
is
a
a
function,
function if there are,
and
if
if
there
there exists, and if
is C and
there
N. Two positive
exists,
constant.
not 2, here it will be 3,
Yeah,
and
okay.
if there exist
C1 and C2
3
should be there, na?
positive
Cons.
constants
C1, C2, G of
C1,
C,
C2 and N0.
N0.
So all I will write with mouse, and we get,
Hmm.
sorry, and we get another function g of
G
n,
of N.
such that such that say, let me write it, c1 comma
C2,
c2 and
N0.
n0. It will be n0, huh? So fn is a function, and if there exist three positive constants c1, c2 and n0, and we get another function g of n such that
It is the function can be defined as big theta.
c1 multiplied by g of n
Hmm.
is less than equal to f of n,
N0.
no, f of n,
Okay, F of N. Then
which is less
C2,
than equal to c2
C2
multiplied by
multiplied by G of N,
g of n for all
N
greater than, for
then
all
N
n
greater
greater
than
than equal to
N0.
n0. And that's all. Very simple.
Mm.
See, till now we are mentioning only one part. Na? Here you have a
Yes,
complete range.
extended part.
So
Mm.
Fn, this will be your, that means
Upper
this is
bound and
your,
lower bound.
this will tell your what, lower
It
bound,
will tell our
that
it.
Fn, it should always be less than equal to Fn. That means
Mm.
it is the lower bound,
Mm.
and Fn
This the
will
other part
always
is
be less than equal to this one. So this will be your upper bound.
upper bound. Mm.
Okay. So when you are multiplying Gn with C1, it is giving you the lower bound of Fn. Now, when
Mm.
you are multiplying the same function Gn with another constant C2, remember these are the constants. Okay.
Yes.
When you multiply the same function Gn with another constant C2, it is
It will
acting as
make
the upper
give us the upper
upper bound.
bound.
Okay. So the formal graph, if I have to draw a graph for theta,
No, the values directly we did it for the previous one.
which one? Yeah, first I am writing this one. Yeah.
Is your screen stuck or what? Because I'm not able to find anything what you're drawing on that.
Right. Just a minute. Is it not
No, it is the screen is paused, I think. I'm not able to see the graph. I think so. You're plotting a graph.
okay? Let me share it once again. Just a minute.
Okay.
Is it visible? Hello.
It is paused. Means yes, yes. I could view the graph now.
Okay. So this was our Fn. Okay.
Hmm.
This is our Fn. Now if I multiply, if we multiply, we are able to find, we are able to find the gn. Okay,
Mm.
so if we are, this is the upper bound, na? So if
Ha.
we are multiplying the gn with
C1.
c2, then this will be your upper bound. Okay,
Yes.
now suppose you are multiplying it by some other constant
C1.
c1, so this will be then the lower bound.
Lower bound.
Okay, so if this happen, then we
Mm.
can say, we have not completed the lemma here,
Okay.
then we can say what fn
Function
is
of
equal
f.
to
F of n.
f of n is equal to theta
Big
of
theta of
g
g
of
of
n.
n.
This is called theta. Fn is equal to theta of g of n.
Mm.
Okay, tell me if it is okay or not.
Yes, it's fine.
This is your n and that will be your t. Okay, now see, take an example for these two. Say fn is equal to 3n plus 2. Okay,
Mm.
so we have to find the theta for this fn. What will be the theta? What will be the theta for this function fn? So what we
Mm.
have to find? We have to find c1,
C1, C2,
c2,
N0.
gn. It is echoing something.
Sorry.
Means my voice is echoing from your device, I think.
From my device, it is echoing.
Mm-hmm. So here, what will be the value of gn? We are taking the value of gn as n, and what will be the value of c1, c2, and n? We have to guess. Say n0. Sorry, it will be n0. Okay. So I think if we put n0 equal to 2, say what we have to find? We have to find 3, sorry, something like that. C1 multiplied by n is less than equal to 3n plus 2 less than equal to something multiplied by n for all n greater than equal to n0. N0. This will be your N0, this will be your C2, and this will be your C1. So N0, if you took N0 as 2, then what will be the value of C1 and C2? C1 may be 3, and if I put 4 here, now see if this inequality satisfied. So if I put n is equal to 2, then this will be your 6 less than equal to uh, 6 plus 2 8 less than equal to 8. So it is okay na. If I put n equal to 3, then this will be your 9 less than equal to 11, 9 plus 2, and less than equal to 12. So it is also okay for n is equal to 3, and this will be okay.
Yes.
Okay,
Yes.
so C1 will be your 3, it will be 4. See, for this function fn, we are able to find the value of Gn, C1 and C2 and N0 such that this condition satisfied. Okay. Hence we can say that our Fn is equal to theta of g of n. Now what is g of n here? That is n. So theta of n. Okay. So we can say for this function, this is our function. For this function, our upper bound and lower bound range, or the upper bound and lower bound, is your theta n. So this was the theta, and these three were called asymptotic notations we used for representing time complexity for any algorithm. Okay, tell me if you have any question. Please unmute.
It is 9:10 already. So
Mhm.